Let me just introduce myself for those of you that don't know who I am. I'm Simon Hanmer. That's not the important bit. The important bit is that I'm a professional geologist of almost some 40 years experience, and also a very keen amateur astronomer of some 20 years experience. And this has led me to combine my two loves in the scientific realm into the field of planetary geology. And my theme for tonight's talk is going to be uniformitarianism, it's not an easy one to pronounce, versus catastrophism on a planetary scale within our solar system. And this idea here, let me explain to you just what uniformitarianism is. In the geological world, back in the 18th century, when geology actually became a science, there were two fundamental laws were determined. One was the law of superposition, which says that something that's actually on top of something which is underneath is probably younger. But the key law that I want to bring to your attention is this uniformitarianism, which says the present is the key to the past. In other words, the processes that we see going on around us today at a planetary scale or other geological scales, these are the processes which probably operated in the past. And it's been a great law. It's really actually helped understand when we look at rocks. But it also turns out to be a shackle. It's also impeded the advancement of science. That's what I'm going to show you. So this theme of uniformitarianism versus catastrophism, this is what's led me to Mars, the real planet, which I didn't actually get to, but I would have liked to. And Mars in inverted commas, which I'll tell you about in just a while. I had to go 14,000 kilometers round trip to actually get to Mars in inverted commas. And the story I'm about to tell you is about my trip. And Mila, I'll try not to speak too quickly, and I'll try to enunciate well. So let's start with the first slide here. Let's go to the next one. So here's Mars. For those of you that don't know Mars very well, Martian geography is quite simple. This is a Mercator projection with the north and south poles cut off, so the actual surface areas are distorted. But you've got this area here of reds and oranges and greens here. These are the highlands. If you like, this is the mountainous area. And in the north, in the blue there, are the northern plains, much lower down, flatter. And the major features of Mars include a huge plateau here called Tharsis, just in case I actually slip into mentioning it. But the real key thing here is this thing called the Mariner Valley. And the key thing to point out here is that, to give you a sense of scale, that Mariner Valley goes from the equivalent of Vancouver to Halifax. That gives you an idea of the scale that we're talking about here. There are also volcanoes, like over here. These large volcanoes over here, these white things, those are volcanoes. And this is the largest volcano in the entire solar system. I'm not going to burden you with names. There are large holes here. These are impact basins, where large meteors or meteorites impacted, asteroids probably, impacted on the surface of Mars. But the real key area I want to talk about is in here, because what I want to talk about today are channels. Let's go to the next slide. This is the area I'm talking about. Not this big channel here, this Mariner Valley. As I said, it's the size of Vancouver to Halifax. The channels I'm interested in here are these ones here, these ones here. There are many more, but I'm just showing you the most obvious ones. There's another one up through there. And these things are called outwash channels. Why are they called outwash channels? Because people think that water coming out of this huge channel here probably flowed out through these to escape from here and end up on the flat floor in the northern part of Mars. There are some who even think that maybe there was an ocean. That's still much up for debate as to whether that's the case. NASA would love it to be the case because they're looking for standing water so that they can continue with their mantra of follow the water, find life, find more money for more research. Let's go to the next one. So let's have a look at some of these outwash valleys and see what they're actually made of. This is a typical example. This one is just under 1,000 kilometers long. Again, I'm not going to burden you with names. The most important thing is it's not exactly straight, it's kind of squiggly, but not much. It's got some curves on it. It's got a flat floor. I'll show you a better example of that in a minute. These flat floors are really characteristic. The key thing is the walls on either side are almost vertical. And the kind of height we're talking about for these is up to 400 meters. So imagine these walls are about half a kilometer high. This The other really key feature is you notice that there are no tributaries flowing into the valley. If you look at the St. Lawrence River, the Ottawa River is a tributary to the St. Lawrence River. The Rideau River is a tributary to the Ottawa River. These valleys have no tributaries. How could they possibly form? By the way, just as an aside, that is Gusev Crater, and that is where one of the first ground rovers from NASA landed. That's the Spirit rover, and apparently it's still there. I'm not sure if it's still moving around. Next one, please. So here's a different perspective here. This is a sort of 3D oblique perspective, but it's real photographs. That's probably something in the order of several tens of kilometers across. Again, these very steep walls here, about a half a kilometer high. Now, you can only see a segment of this particular valley, but take my word for it, all the way along its length, there are no tributaries. This is really key. These grooves along its length here, don't worry about those. Those are quite late with respect to when the valley was formed, and they're probably the result of glaciation, glaciers moving. Yes, Mars had glaciers. Okay, next slide, please. So I've shown you some gently winding, flat-bottomed, steep-walled valleys, but there's another kind of outwash valley as well. Notice how squiggly this one here is, and that white box is this blown up. And you can see that essentially it still has a flat bottom. It's got almost vertical sides, again, about a half a kilometer high. You might look at that and say, well, that's probably a river because it looks like meanders. But compared with the river on Earth, these meanders are rather chaotic. They suddenly switch back on themselves in a way that terrestrial meanders don't do. There is a river actually in this valley. It's just that thing there, or a river valley within a valley. Okay, next slide, please. Now, the best studied on Mars, the best studied of all these outwash valleys is this one here. It's quite complicated. It's called Kasei Vallis, and Kasei basically is the Japanese word for Mars. And you can see it's actually 2,000 kilometers long. It's tens of kilometers across, possibly even in places 100. And you can see it's quite wide down here at its southern end. And then it divides up into all kinds of branches which seem to flow around high-standing ground that's been left behind, remnants from the erosion. Next slide, please. So it turns out that the very best evidence for how these things formed in this best described of all the Martian outwash valleys is even down here. It's an even more restricted area, down almost at the mouth of the valley. And again, you can see how the channel comes up, and over here it divides down here around this island here. There's a high standing island, a lower standing island. This is actually a large island in itself with a crater in the middle of it. And then out here, up in that top corner there, you can't see it on this here, but you will in the next few pictures, there are islands, remnant islands of sediment which have been left behind from the erosional processes. Next one, please. Okay, so this is a photograph of the picture I just showed you in the red box. And again, I said there's a high standing island, there's a relatively low standing island there, and there are, that can go away, there we go, and there are these rather smooth elliptical looking features over here, which again I'll show you the details of in a moment. But these are islands of sediment, and this all here, this is volcanic rock. This is really important. This is volcanic rock. Mars is made essentially of volcanic rock which resembles the rocks which make up the ocean floors on Earth. And it's called basalt. Again, we don't need to get into technical details, but I want you to just remember the idea of basalt lava. This is sediment which is sitting on top of the basalt lava, and when it gets eroded, it looks different from the way that the basalt erodes. That's the reason for me showing you this slide and pointing this out. Okay, next one, please. So we're going to go to here. Next one, Sleep. Have we crashed? Oh, no, that's good. That is excellent. So here's the high standing island, here's the relatively low standing island, and you notice that in these three boxes here, there are these scallopy features. And there we go, it's a little more difficult to see in that one, but you can see them up here too. And the key thing is that these are indentations, if you like, in the cliff walls. This is the valley floor, and here's the valley floor coming up. Remember, these valley walls are half a kilometer high, and that dimension is 100 kilometers. So what are these things? They're waterfalls. These are waterfalls half a kilometer high in sets, one next to cheek by jowl with each other. here over a distance of 100 kilometers. They're dry now, obviously there's no water. So if we go to the next slide, think Niagara Falls. Niagara Falls today is made of wet areas where the water is actively flowing, separated by essentially dry rock. So you've got two waterfalls, at least in this picture, cheek by jowl. Now imagine maybe 15 of them over a stretch of high cliff of 100 kilometers in length. This is probably of the order of 50 meters, 50, and we're talking up to 500 meters on the equivalents on Mars. The ones on Mars are huge. Next one, please. Now can we go back actually? You probably know that Niagara Falls is gradually migrating its way upstream. What's happening is that as the water comes over this lip here and the same here, the rocks get eroded very slowly. And so the waterfall migrates back upstream, which is in this direction. And it's migrating back upstream at about 1 kilometer every 1,000 years. That's a normal rate of erosion. I just want you to remember that. 1 kilometer every 1,000 years. Next slide, please. Here's what geologists, planetary geologists tell us is the direct equivalent of Niagara Falls on Mars. Here's a couple of large waterfall cataracts, if you like, and there's a couple of small ones here. And the idea is that they were originally down here, and that with erosion, they recessed, they receded back upstream in this blind box canyon. That's great, except that that's 200 kilometers. That's a long way. That's a lot of upstream erosion. Next one, please. So those were features that you can actually see on Mars as erosions taking place in basalt, which people usually think of as pretty hard, tough stuff. Here's up in that northeastern corner of the big picture I showed you, where you've got these elliptical forms here. And just so that you see what's going on, the light is shining from this side. So all the bright areas here, those are high-standing cliffs of the order of a couple of 100 to 400 meters high. And the shadows, the dark areas, those are shadows. There are all these sort of fish shapes here, and they're called streamlined remnant islands. This is the way that the sedimentary material reacts to the same kind of erosion, and we'll get to what it is that's doing the eroding in just a minute, as actually formed the cataracts or dry waterfalls, which are called cataracts, on the previous slides. These things here can be clearly in the order of hundreds of kilometers long and 10 kilometers or more across. So again, they're really large features. Next one, please. So what is it that the planetary geologists who have been spending a lot of money and a lot of time studying Mars are going to tell us about how these channels formed and the various features that are within them? Well, what they suggest is that there were these incredibly powerful, rapid, catastrophic floods that occurred. That water somehow was released across the surface of Mars in almost an instant, flowed across, did the work of eroding very, very quickly, and then disappeared. Now, it sounds like magic, but in fact, water could disappear in all kinds of ways. It could actually disappear through the atmosphere. Mars's atmosphere is very, very thin. It could end up getting into the bedrock and then freezing as permafrost. Canadians know all about permafrost. There is permafrost on Mars, and the Mars has lost some of its water through the top of its atmosphere. But the reality is that they don't really know where to get the water from in the first place. We're talking here about channels which were formed about 2 billion years ago. The solar system was about 4.5 billion years ago, so if you think of this as a hockey game, these channels formed at about the halfway mark in the hockey game. The trouble is that nobody really thinks that there was surface water on Mars at that time. They think that any surface water that really occurred sometime in the early part of the first quarter of the match. Gives you an idea of how far removed the possibility of water on the surface is from the formation of these channels. So why do scientists think that these things form by catastrophic flooding rather than slow erosion by little bits of water that might have gotten onto the surface, rather in the same way that Niagara Falls formed? 1,000 meters of erosion every 1,000 years. It's computer models. They can make a number of assumptions. I won't get into the details of what those assumptions are. They can make a number of assumptions which are indeed almost guesswork, run it through the computer model and say, oh look, here's the result. But you know, science isn't supposed to work that way. Science is supposed to start with at least some observational evidence. some observational evidence that you can either repeat in the laboratory or you can actually go out and observe it several times out in nature. So what is their observational evidence? They don't have any. Instead, what they do is they point to an analogous situation on Earth. There's one place on Earth where the scientific community generally considers that the geology of this particular place on Earth is a direct analogy for what we see on Mars. And this is where I felt I had to go. I wanted to see for myself this analogy with channels that I was never going to manage to actually set foot on myself. By the way, this is an artist's impression of what the channels would look like on Mars. It's pretty good. Flat-bottomed, really steep walls going up hundreds of meters. He couldn't tell us whether or not there were tributaries from this. Be aware that there are several kinds of models. The planetary scientists will tell us that it was water, catastrophic floods of water that carved these channels. But there are others who say, well, we're not sure. Maybe it was actually flowing lava itself that actually formed the channels. Now, that's definitely an alternative minority model, but it's not off the wall. There are serious scientific, there are serious scientists in the university community who are proposing that. We'll deal with that in just a few slides. So let's go to the next one. So where is this analogy on Earth, this one analogy that exists? Well, it's in Washington State in the northwestern US. And the story goes like this. In the northwestern US, in this brown area here, this is what's called the channeled scablands. And the channeled scablands are made up of horizontal flows of basalt lava, hence one of the analogies with Mars, which are 15 million years old approximately. Don't worry about these numbers, they're out of date, but it was a nice slide. And the idea is, the story is, that there was an ice dam across what we would now call the Columbia River today. An ice dam about 15,000 years ago, so a long time after these basalts had actually been erupted. And this was part and parcel of the glaciation in North America, which actually lasted from about 2 million years ago to about 15,000 years ago. So we're looking here at an ice dam almost at the very end of the last great ice age. And that ice dam, by blocking rivers trying to flow out to the Pacific, actually formed a large lake. And it's called Glacial Lake Missoula, after the town of Missoula in northwestern Montana. And the story is this, that about 15,000 years ago, that ice dam suddenly broke. Water probably got underneath the ice dam. This lake would have been 700 meters deep, and in surface area, the equivalent of Lakes Ontario and Erie together. So a lot of water, a lot of pressure at the base of the dam. And the idea is that the water would lift the dam, and of course, as soon as the dam is lifted, and it's an ice dam, it breaks catastrophically, and water just tumbled out towards the Pacific. And what we're going to do is we're going to have a look and see just what the evidence for that really is. So let's go to the next slide. This idea all came from this gentleman, Harlan Bretz. Harlan Bretz first came up with this idea back in the 1920s, and he was told, impossible. Why? Because of the law of uniformitarianism. In the 1920s, nobody was thinking about asteroids being responsible for the death, the extinction of the dinosaurs, for example. There was no room for catastrophe. So he was laughed out of court. The other thing was, they said, well, where's your water? And he didn't know about Glacial Lake Missoula at the time. In the 1940s, they began finding evidence for Glacial Lake Missoula. And then in the 1970s, he was vindicated for two reasons. One is they actually started flying really good aerial photographs of the northwestern US. And the first, was it Voyager or Mariner that actually the first probe to arrive at Mars and send back pictures? I can never remember exactly what the name was. Mariner. It started sending pictures back, and as soon as they saw the pictures, again, around about the same time, they said, oh my God, that looks just like the channeled scablands of Washington State. So that's when the idea first was mooted that there's a direct analogy. And people don't seem to have questioned that much since then. So let's go to the next slide. So I got in my car, this was last August, and I drove. I decided to take the Trans-Canada Highway. I've never driven across Canada. I think every Canadian should if they can. I did, and I really loved it. This is the kind of scenery that I was seeing as I came through Ontario, these huge, gigantic road cuts, where the geology is just laid out for you. And even at 100 kilometers an hour, I could interpret it, not in detail, but I could interpret the general story. This was a real thrill. Next one, please. I always thought that Northern Ontario was just a corridor of jack pine, that you could see nothing other than what's right in front of your windscreen, but boy, was I wrong. Fantastic vistas like this with this rolling topography. I'm still in northwestern Ontario here. Next slide. This is the prairies. Boy, what a change. Well, I'm standing here on a very slight rise at a rest area, and you can see the curve on the horizon. But you know, the strangest thing that I found was actually the people. I love Manitobans. I know lots of Manitobans. I have very good friends. Some of my best friends are Manitobans, to coin a phrase. But boy, they have a very strange way of driving. On the Trans-Canada, they all drive at exactly the speed limit. And they all drive with cruise control. So to overtake you, as opposed to actually overtaking, it's more like a shadow moving across the sundial as the sun is actually moving across the sky. So that's fine. I have no problem with that. But then they would get in front of you. And instead of going down the highway, you can see 10 kilometers in one direction and 10 kilometers behind you. Instead of going down for another 100 meters and then pulling in front of you, no. They're going 1 kilometer an hour faster than you, and 15 meters in front of you, they pull in. Okay. But they all did it. And the Albertans and the Saskatoonians and what have you that were driving across Manitoba, they overtook me normally. But here's the really weird bit. When I crossed the border from Manitoba into Saskatchewan, those Manitobans, they sped up and they overtook me as normal people do, pulled in front of me about 100 meters down the road. I don't know. I can only assume that somehow or another it's got something to do with their driving schools. Anyway, next slide, please. This is a Google shot around Medicine Hat of the prairies, and my God, you can see it is flat. Not a tree to be seen. Next slide, please. And then all of a sudden, you pass Calgary and you're heading towards the Rocky Mountains, and the Rocky Mountains just leap right out of the plain, practically. It is astounding. I mean, I know geologically why it's happening, but I'm not going to get into the details of that. There's actually a big fault. If you go to the next slide, we can actually see this again in a Google Earth shot. I was about there taking that photograph, looking at the mountain front itself, but there's actually a clue that you're coming to the mountain front. These are this is the fallen area of the Rocky Mountains. They're rolling hills. And then this is Calgary itself, by the way, for scale. And then this is the prairies out here. So there's the Trans-Canada Highway, and I drove into the mountains. Next one, please. So there I am. I finally got into the mountains. And this is one of my side trips. And this is going to be to show you the first catastrophic event that I went to study. This is Yoho National Park. We're here in Kicking Horse Valley. This is the Kicking Horse River. Yoho National Park. And I'd gone there to see the Burgess Shale. What is the Burgess Shale? You've probably heard that the story of life on Earth is that, frankly, life has been around for about 3.5 billion years, but it's been sort of single-celled algae, maybe a few jellyfish floating around, maybe a few worms, but nothing with any really detailed body parts like legs and heads and eyes and what have you. And then there was this thing called the Cambrian explosion about 550 to 500 million years ago. And everybody thinks, oh great, that's when we actually started getting complex life with bones and shells, and so now we get lots of fossils. But it wasn't an explosion. There were multiple explosions. And they weren't local explosions, they were global explosions. And what I went to see was the Burgess Shale, which contains the weirdest fossils you've ever seen. And they only lasted for maybe 10 million years. And then, wow, extinct. And they didn't just occur in Yoho National Park, they occurred all over. The Burgess Shale equivalents are known in China, they're known in Argentina, I believe they're also known in Africa. So this is a global population that all of a sudden was wiped out. Now, how do you wipe out things on a global scale, especially when they're actually on the bottom of the sea, bottom of the ocean? It's got to be something really catastrophic, whether it's external to the planet, so a big impact that actually hits the planet and creates mayhem, or you could actually have vast outpourings of lava, which could then put a lot of CO2 into the atmosphere, and that could change the entire climate. You could also put a lot of sulfuric acid into the atmosphere. Nobody actually knows. But we know that it was something catastrophic. Go to the next one, please. So let me just show you. In order to get up to see the Burgess Shale, I had to hike for 10.5 hours up into the mountains with a guide. And this is on the way up. This is some of the scenery we were seeing as we were headed up. Just keep an eye on that sort of U-shaped structure there. You'll see it again in the next slide. This is the Burgess Shale right here, this black patch there. and it extends off like this out of the picture. There's that U-shaped area that I just showed you we walked by. And we came around like this and then scrambled up the slope to get here. Apparently the fine for taking any of the specimens from this area is $5 million per specimen. It ain't worth it, you know. Anyway, this was absolutely amazing. The actual quarry itself is probably no bigger than this room. And the quarry face might be the size of the height of the wall here. But it was absolutely amazing. Let me show you some of the stuff we could see. Next slide, please. These are sponges. Imagine a bath sponge. Well, this is a collection of them. And the detail of preservation here is so good that you can actually see little bumpy parts on here. And those are the actual cells of the animal that made up the sponge. Next one, please. This is a worm. You've all been to the beach and you've seen these little piles of droppings, and next to the little pile of droppings is a little hole because the worm is in a U shape underneath. Well, that's what this is. And that's probably about that long, I would say. They're what, 6, 7, 8 centimeters? And if you look in here, that dark area there, that's the gut. Next one, please. Here's a segmented worm. I'm not sure whether that's the head or that, but you can see the segments, and you can actually see little leggy things coming off it. Apparently some of the early worms had legs. And again, look at that black through there. That's the gut. And I wonder, is that an antenna? Let's go to the next one, please. This looks like a shrimp, but there weren't any shrimp at the time. This is not even a proto-shrimp. This is something which simply lived in a similar environment and therefore adapted similarly to it. And the head has been lost, but that is absolutely remarkable. And these are photographs that I took actually in the quarry. Next one, please. I put the word squid here. It's not actually a squid. I thought it might be. I thought that might be rather like an equivalent of a cuttlefish bone or something like that. But, all right, I won't ask you again, or don't ask me again. There we go. The animal actually lived here, and apparently it dropped itself like a dart into the mud of the sea bottom, and then it just grabbed anything that was going by. I don't think it actually had tentacles like a squid, though. But that's about 3-4 centimeters long. Next one, please. Can we get the next slide? There we go. This bug here is, again, it's segmented. It's about the size of a small child's hand. It sort of resembles those little creatures that scurry around in your unfinished basement, especially in the wet areas. Next one, please. This is the classic trilobite. This is absolutely beautifully preserved. But I show you this because this one is beautifully complete. If we go to the next one, this one is the size of my hand. And it got squished, not by somebody stepping on it, of course, there was nobody around to do that. It got squished by the overlying sediment. And the reason I'm showing you this is if you look at the body here, see these spines coming off? See how they're beautifully preserved? And the same spines are over here too. Absolutely fantastic preservation of these animals. Let's go to the next one. This is absolutely remarkable. When this was first found, they thought it was a shrimp. But it turns out to actually be one of the mouth parts of an animal about 1/2 meter long, probably the largest animal in the sea at that time. And it had 2 of these, and one on either side of the mouth, and these things were like feathers. And they're not really sure if these were some kind of grasping claws for a predator, or if they were like brushes to actually sweep a smaller prey into its mouth. And if we go to the next slide, this was thought to be an independent creature. That's the mouth of the animal that had the claw-like features that I just showed you on the previous slide. And there are teeth in there. They're not preserved in this particular specimen, but that's where there were teeth. So that was like a muscle which would close and actually ingest food. Okay. So that's just taking you through rather quickly some of the creatures. What I do want to pass around, these 2 photographs. No, they would not let me actually see creatures like this actually in the quarry. These things are worth a fortune. But this one here, this is an animal called hallucigenia. It's so weird that it looks like a hallucination. Okay, let's go to the next slide. Well, having been up to on my first side trip and seen the first catastrophic event of my trip, I didn't have a catastrophe, luckily. I had a really pleasant hike. I then set off south through British Columbia, down what's called the Rocky Mountain Trench. And what this is here, this is a long valley which goes right the way down into the United States. It goes from almost the Yukon border with Alaska. And on this side here, you've got the Rockies. That's the east side. And on the west side here, you've got the interior mountains of BC. And so I just drove straight down that valley, down into Idaho, and then on to northwestern Washington State. Next slide, please. And here I am. You can see that these little yellow pins here, they indicate the kinds of areas that I'd planned I was going to go and see. There's actually more outside of this picture here, but I wanted you to see Moses Lake. Moses Lake in northwestern Washington, or western Washington, that's where I stayed for 2 weeks, and I radiated out in all directions. So from Moses Lake to about here would have been about 150 kilometers, that kind of thing. So let's go to the first slide. So here we are on Mars, in inverted commas, in Washington State. These are known as coulees. It actually is the French word coulee. And when I used the word coulee, nobody knew what the hell I was talking about. So I had to remember to call it a coulee. These things here are flat-bottomed, wide, vertically sided, long channels with no tributaries. The difference is that this is the longest one. It's called Grand Coulee, and it's 80 kilometers long. Whereas Casey Valley on Mars was 2,000. These vertical walls can go up to 150 meters maximum, but they usually average out around about 100. And on Mars, it was half a kilometer. The width here is a couple of kilometers maximum, whereas on Mars, it was tens of kilometers, maybe even 100 locally. So that gives you a perspective along Grand Coulee. I'm looking upstream here. We're not going to worry about geographical direction. Next one, please. This is looking downstream the other way, and I put this in so you can actually see the horizontal lavas. And these are the walls here that are in the order of 150 meters high. Notice how the valley curves gently. It's not squiggly, but it's not dead straight. Next slide, please. Now, those lavas, remember, they're 15 million years old, so they're much older than the erosion, which is 15,000 years old. Keep that in mind. So here's another one of these coulees, and you notice I'm on the flat floor here, and there are the vertical walls, and you can see the lavas beautifully here, the different lavas. But notice the valley goes in here, and then it suddenly turns. So it starts getting squiggly, like I showed you on Mars. Let's go to the next one. As you go right down towards the southern end of the area that I wanted to look at, there is a range of relatively high hills, and this is actually the Columbia River going through. And these hills and the Columbia River were a barrier. The Columbia River wasn't wide enough for all of this water, which I'm going to be talking to you about in a minute, this flood water, which created these huge coulee outwash channels, couldn't get through. And so it piled up here and formed a new lake, not Lake Missoula, but another lake, which eventually managed to rush through that gap there. The really important part of this story is that, and I'm going to show it to you, is that this catastrophic flooding occurred in 3 to 7 days. That's catastrophic. Next one, please. So, what have we got here? We can actually see time in the formation of these valleys. Here we're in Grand Coulee. There's the flat floor. There are the vertical walls going up to 150 meters. But what's this? That's another outwash channel, but it's high perched. It's called a hanging valley. And we've definitely got a time sequence here. This thing here, which is a outwash channel in its own right, flat bottom, vertical walls, very slightly not dead straight, formed before the main channel. And as the main channel formed, it dug down even deeper and left this channel abandoned. So this was the first channel, and this was the second. In other words, this is not a tributary. It's older. It's nothing to do with the story of this channel here. So we've got a time sequence. But here's the important question. How much time? Are we talking about slow erosion like on Niagara, or are we talking about the catastrophic flooding that the planetary scientists really want us to find in order to interpret Mars as they see it? So the question is, which we will be addressing, is what will be the actual observational evidence for rates of erosion? Next one, please. Now, these valleys are very precise. Vertical walls, flat floors, either wiggling or gently curved. How do you carve something that precise in solid lava? And the answer is you don't, because the lava is not solid. Look at these lava flows here. There's a couple of lava flows up there. There's a big one here. There's another one down there, and there's another one below it. This is about 50 meters. And you notice all these fractures through here? These are called columnar joints. And what they are is they're the result of the lava cooling. As the lava cools, it comes out onto the surface quite quickly. It cools quite quickly, and it'll turn into rock. And as it does that, it shrinks. It doesn't shrink the way that your best cottons might if you put them in the wash at the wrong temperature, but it shrinks, and it shrinks internally, not just the edges. And as it does so, these fractures form. And if you look down on these fractures from above, they form hexagons, as the lava is trying to actually pull in around a particular point. And then there's another hexagon as the lava is trying to pull in around that next point. So these are really quite finely spaced. Let's go to the next one. There are some pretty big ones too. These are columnar joints up here. You can see the cars for scale. See that? Those are people. They're climbers. They're actually trying to climb up the face of these individual columnar joints.
Can I ask a question or shall I later?
No, you can ask me a question.
Say again why they form in a vertical
I'll
column?
explain that later.
Okay.
Okay, let's go to the next slide. So, okay, we've got our geometry, we've got our channels, we know that the basalt, frankly, is not rock solid. It's actually rather like a bunch of Skittles. In other words, you manage to knock a few of these joints out, and then all of a sudden you've now got access to the rest of the lava, and out it comes. But how do you actually get this precise geometry? Well, here it is. What you've got here is a dry waterfall, a dry cataract. This is not the waterfall that formed it. This is just some modern trickle. The actual dry waterfall was that wide, and the water was that deep, and would be flowing into this canyon here downstream. See this little erosional remnant there? And with the little vertical columns in it? That's an erosional remnant of the lava, and that's why I talk about Skittles. It even looks like Skittles. This is, again, is on the Niagara perspective, this would have been, this is the equivalent of a dry waterfall. Let's go to the next slide. If you look downstream from that dry waterfall, you see this fantastic canyon, vertical sides, multiple lava flows, and again, you can see it getting really quite squiggly. The interpretation here, based on field evidence, is that these changes in direction, sudden changes in direction of the outwash channel are due to pre-existing older cracks and faults. Now, all you have to do to take this image to Mars, next slide, assuming that you have those same kinds of cracks and faults, is to take the previous image and simply round off some of those squiggles. They were pretty sharp-cornered on the terrestrial example, but you've got lots of time on Mars to round them off, and you can end up with these squiggly, river-like looking channels. Next slide. So let's take a look at the very best example of these dry waterfalls. It's called Dry Falls, and it forms about halfway along Grand Coulee. You can see this plain here. This plain goes just out to the horizon. The whole area looks like the prairies, except the prairies are not underlain by basalt like this. And this here, this is the equivalent to one of the Niagara waterfalls. This is the dry cataract. Keep an eye on that little white patch there. It'll come up in the next slide. Go to the next slide, please. There it is there. And what you've got, this is the right-hand side of that cataract I was just showing you. There's another one behind it. And here in the foreground is a remnant spine of rock which separates one cataract from the other. And if we go to the next slide, you'll see this as I pull back. There it is. There's the spine of rock going from there to there. That's about 1 kilometer. So we've got two waterfalls which are receding upstream, and upstream is to the left. And as they recede erosionally upstream at whatever rate, there's a remnant of rock between them, which is called a rocky blade. And that's what we can see here. And you can, again, you can see how this has been incised down into the plane at the surface there. Now, the importance of this is that these kinds of features occur everywhere in the channeled scablands. As soon as you get into one of these coulees, you are probably going to find these paired cataracts and this rocky blade here. It is absolutely essential to the formation of these outwash channels. And I'm emphasizing that point for a very good reason, which I'll come to in just a moment. So, okay, we've now got the mechanism and we've got the geometry. Now, what about the rate? We'll come to whether it was really water or not in just a minute. Let's go to the next slide. Oh, by the way, before I forget this here is the iconic Steamboat Rock, which is probably the best known tourist icon in the whole of Washington State. And what that actually is, that is the largest remnant spine of rock between two waterfalls, which were migrating upstream that way. The waterfalls have gone so far upstream that they completely abandoned this spine, and it just sits out here. It's about 110 meters high. Next one, please. So what is the evidence in Washington State for catastrophic rates of erosion? Well, it's surprising. It's none of these big spectacular features. It's not 100 meters high. It's these things, these boulders, which are boulders of basalt. They're about meter and a half across. And you can see they're spaced at, well, no more than about 2 meters away from each other. See, we can see out to the horizon here? Well, this is a plain. And you can see for 10, 15, 20, 30 kilometers all around. And this plain here, called the Ephrata Fan, don't worry about that, is at the southern end of Grand Coulee, which is the biggest coulee in Washington State. They don't occur anywhere else. And the interpretation of this is that this is the shot, which was blown out of a natural shotgun. And the natural shotgun would have been the Grand Coulee Canyon, filled to the brim with water flowing at 110 kilometers an hour, and would have carried these things. You couldn't simply roll them over the ground in order to cover this huge area. You had to blow them out. In other words, they were airborne. Airborne in a shot of water coming out at fantastic rates. You wouldn't be able to see this kind of thing on Mars even if it's there, because our current platforms and optics of cameras that are going around Mars cannot detect things at this size yet. Let's go to the next one. Here's another piece of evidence, potholes. See, there's a breached pothole there. There's another pothole there. Now, these are small potholes. I managed to get up onto a cliff so I could actually photograph them. To photograph the big ones, and by big ones, I mean the size of the car park outside where you parked your cars. That would be relatively small. Those ones you've got to get into a helicopter, because there's no way you can get into a position to actually photograph them otherwise. But they are everywhere too. So with this kind of evidence, people can sit down and say, well, just what kind of force does it take to create holes like that, in that kind of rock, to actually lift and throw boulders of basalt, lava, over tens of kilometers, almost through the air? What kind of force do we require? And what is actually the piston behind that? But there's another piece of evidence as well, which I don't have a picture for you for. These channels are loosely connected with each other. And it turns out that the upstream channels, in some cases, their floors are lower than the floors of the downstream channels. In fact, they're lower than the tops of the downstream channels, and sometimes by 100 meters, which means that the upstream channels had to be filled with at least 100 meters of water before anything even trickled into the next channel, let alone carved another channel 100 meters deep. So you've already got 100 meters upstream, another 100 meters downstream. You've now got a column of water 200 meters deep. And you know that you've got to use that to actually create these giant potholes and throw this shot over tens of kilometers. And that's what allows those that could do these kinds of calculations to actually turn around and, based on observations, say, this is the kind of conditions we needed to see. Next slide, please. Now, how do we know it's water? After all, I mentioned that on Mars, some people have suggested, well, maybe it was these things were carved by lava, really liquid, runny lava. Well, here's the answer. This is an example of an island of sediment which resisted the flow of water. And it has this characteristic asymmetrical shape with a steep slope here and a shallow slope there, telling us that the water flowed from left to right. That's a relatively small example. Let's go to the next one. This is a larger example, steep slope, shallow slope. And the important thing is that this sediment here, and we know it's sediment because that's what's being farmed for wheat. You can't grow wheat on basalt. It's as simple as that. So if this had been anything other than water that had carved these islands, then there would be a sheath of basalt lava, both on the floor here and over the top of the island, and it is not. Next slide, please. And here's an even larger example. See, we're still not at the scale of the equivalents on Mars, which could be hundreds of kilometers long. This one's probably a couple of kilometers long. But you see how they're sitting on the plane. You do actually also find these things down in some of the channels, but the importance about them being on the plane, you'll realize in just a moment. Next, go to the next one. What else it tells us that the water was involved? Well, here we're actually in the Columbia River, and it actually is a coulee. It's one of these outwash channels. Flat floor, very, very steep sides. And this is a sandbar on the inside of a bend in the river. Notice these bumpy things here? Let's go to the next slide. There they are. These are what are called mega ripples. You've all been to the beach and you've seen that ripply texture as the sand gets ripply. Well, that's what these are, and that would be easily 50 meters across. Only deep, fast-running water could create something like this. Let's go to the next one. And here's a fantastic example. You can actually see this from the Snake River. You can actually see the horizontal lavas, which were then into which the channel was carved. And then as the water was flowing through the channel, it deposited sand on the floor of the channel, and then it molded the top of the sand into these huge mega ripples. Only water can do this. Wind cannot do this, not at this kind of scale. Next one, please. How deep was that water? This is the water actually sitting on the plane, not the water actually in the channels. This is the water before you've even carved the channels. Well, I'm looking along now, along the axis of one of these remnant streamlined islands of sediment. And you see how there are channels that have been carved in it. In other words, this island was at least temporarily submerged. So you've got to add at least that height of water on the plane itself before you even start to carve the channels. Next slide, please. I love this one. This is considered to be a mega island of sediment. That dimension is about 30 kilometers. That is about 10 kilometers. And there's another one over here, which is a similar kind of dimensions. And this actually is one of these outwash channels carved between them. So you've got really a mega island. But I don't know if you can see how it's bumpy on top. It's not smooth. It means that let's go to the next slide and you'll see. See how it's rolling country? Well, that means that the water overtopped this mega island in order to actually mold again the sediment at the top in these huge ripple-like forms. In order to actually top this island and submerge it, you had to have at least another 100 meters of water on the plane before you start counting the depths of water that was actually down in the channels themselves. So that's how they actually work out how deep the water is. Next slide, please. I'm going to skip this one and over the next one, and the next one, and the next one. This is a range of hills right down at the very southern end of the area I was looking at the channeled scablands. It's called the Saddle Mountains if you're interested. The important thing is that the rocks which are actually making the mountain are solid rock. Whereas this thing sticking out here, this promontory, which actually has a sort of a delta shape. We're looking at one side of the delta, then there's a point, and then it goes back the other way. That's the kind of sediment we've just been looking at with the remnant islands. And the idea here is that the water down in the plain here just rammed down as a sheet, bashed up against these mountains, couldn't top them, and spread this way on this side of that promontory and went the other way on the other side of the promontory, and left this relic here. So the height of this relic here tells you the kind of depth of water that actually hit the mountains from the plain, and gives you an idea of the force that actually managed to carry off all the other sediment around it. So next slide. So let's synthesize. What have we actually got here? We've got a situation where 15,000 years ago, an ice dam broke, and the glacial lake Missoula emptied in the space of 3 to 7 days, and the water headed down towards the Pacific Ocean. It wanted to get into what was then if you like, the Proto-Columbia River Valley, but there was too much water, or way too much water. We're talking about 300 meters deep, flowing 100 meters on the plain, another 100 meters in the shallow channels, and another 100 meters in the upstream channels. And this is, of course, a perspective view of Dry Falls. There is the remnant rocky blade with the cataracts upstream this way on this side. As it flowed, it managed to pluck out these shattered or thermally shrunk lavas and carved out these steep channels, got down to the end of Grand Coulee here and just blasted that shot all over the place. But it's essential in this mechanism that this formation of rocky blades by the upstream migration of Niagara-type waterfalls, cascades, cataracts, that's the essential mechanism for doing the eroding, but not at Niagara speeds, all within 3 to 7 days. Next one, please. So, where are we? I've been to Mars. I got home, of course. Mars in inverted commas. I got home and I went back to the internet. And I said to myself, well, can I actually see the features that I've now seen on the ground? I mean, the thing that I really learnt by going to Washington State was I got a critical perspective, which now allowed me to look critically at the Martian evidence. Well, here's a bit of a problem. That's the only place on Mars where you can see all of the features that I showed you in Washington State, at least the big features, not the small ones. That means that scientists are actually investing an enormous amount of scientific real estate, they're investing a lot of science and scientific interpretation in very few observations. Where are the rest of the cataracts? Why aren't they down this valley, another valley over here, which I actually showed you? Where are they? Secondly, why are the Martian examples so much bigger than the Earth examples? You might think it was the other way around. We've got much more water than Mars has. We've got more gravity than Mars has, so that water will have more of an erosive effect. Why are the Martian examples so huge? And here's the real trick question. Where does that water come from? Some suggest that, oh, there's volcanic activity on Mars in the past, and that volcanic activity gets the permafrost. Remember the examples of glaciation? Gets the permafrost to melt all of a sudden. And that melting water comes out onto the surface and suddenly carves these huge channels. Well, think of it. If I tried to catastrophically flood you, I have a hand basin with water and I do splush like this. Now I try to do the same thing with the same volume of water, but in a sponge. No matter how much I squeeze it, no matter how much I shake it at you, I cannot produce the catastrophic flood effect. And it turns out that scientifically, those who do these things better than me, when they calculate how water moves through porous material, number one, it moves slowly. And number two, we're talking huge volumes of water to do this. So it really is an enormous problem. The planetary scientists studying Mars really have to go back and answer these fundamental questions. As to actually finding observational evidence which might prove or disprove the catastrophic rate of water flow, because everything I'm saying to you about Mars could occur at the rates of recession of Niagara Falls, quite frankly. They've got to find observational evidence for really catastrophic flood rates, and they're going to have to improve the resolution of cameras that are looking at the surface of Mars before they can do that. So we may have to wait for quite a while before we can actually really test that hypothesis. So am I saying that the analogy doesn't apply? No, I'm saying it could. The same processes are going on, but I don't see them occurring in the same ratio, and that the planetary scientists really have quite a bit more work to do. All righty, let's go to the next slide here. Well, it was time to come home from Washington State, and so I drove home via Crow's Nest Pass into southern Alberta. Crow's Nest Pass was fun. I'd never been through there. It snowed, and the snow was right down to the ground, and we were only about the 3rd of September. I had to Google to find out whether this was some kind of disastrous climate change or not. It turns out that no, they actually do get snow at that time of the year. And I went to the Badlands. I went to the Badlands because I wanted to see evidence for another catastrophic event in the solar system. As you probably know, the idea is that the dinosaurs lasted from about 200 and something million years to about 65 million years, and then appeared to become extinct overnight. There are two main arguments about this. One is that there was a catastrophic impact somewhere off the coast of Mexico. And others say, no, what actually was happening was that India was pulling away from Asia. If I got that one the right way around, I think I do. Or something was pulling off of India. And there was catastrophic volcanism from huge volumes of volcanism over a period of maybe 1 million years. And it's that actually killed the dinosaurs off. Then there are others that say, well, it was a mix of both. But the important thing is that they died catastrophically in a geological event. So I went to see this. This is what the Badlands look like. What I'd gone to see was the Tyrrell Museum. The Tyrrell, it's the Tyrrell Provincial Museum. And it is probably the best natural history museum I have ever seen in my life anywhere. This is the wild kind of country. I had no idea why it was called the Badlands until I got there. I thought it was Badlands because it was difficult to farm. But no, it's called the Badlands because these layers here, these are volcanic ash, coal, mud. And the volcanic ash, when it gets altered, it turns into a thing called bentonite, which is a clay. And the strange thing about bentonite is that when it gets wet with rain, it inflates in volume to 10 times its normal volume. Well, you can imagine trying to get a horse and cart through that. And so it was actually the Québécois voyageurs who called it the Badlands because it was bad land to travel. Next one, please. This is actually the Red Deer Valley. And you can see the layering here more clearly. That actually is a coal seam. And I show this picture because the Tyrrell Museum is actually located in something looking exactly like this. This was a better shot than I could get from the Tyrrell Museum itself because there was a lookout here. But you really expect to see John Wayne coming around the corner on a horse here. But the really key thing is that these are the layers that contain the fantastic dinosaurs that are in the museum. And the museum isn't just a building, it's actually this vast terrain they have. And they're actually still digging dinosaurs out of the museum's grounds to actually go into the collection. Next slide, please. That's just a close-up view of what these layers actually look like. And this is actually in downtown Drumheller, which is the town which the museum is located in. Next one, please. So I walk into the museum, and this is what I see. As I say, many of the specimens that actually turn up in the museum are local. This is just the entrance room where you see specimens like this. Let's go to the next one. They're pretty lifelike. I didn't know I was going to get this one almost actually looking at me in my picture. In this room here, I took a few pictures with flashes, but most of the time it is so well illuminated, I didn't need the flash. Go to the next slide. Absolutely magnificent. But this isn't the good stuff. The good stuff's in the next slide. These skeletons, every one of the skeletons is in a life position. And you can see that behind there's a diorama which actually shows the skeleton filled in and the animal doing the same thing. So this is not Tyrannosaurus rex, by the way, some distant cousin. And down here on the floor, you've got a vegetarian dinosaur, which is about to sort of be gobbled up by this creature here that's just killed it. Next slide, please. This is Tyrannosaurus rex. The museum actually has 3 Tyrannosaurus rexes on display. It's the only museum in the world that has this. And this is a triceratops, which I'll show you in a moment. It's like a rhinoceros with 3 horns. These things are huge. Next slide, please. So there's Triceratops now with its 3 horns coming out of its forehead. And there's the back end of Tyrannosaurus rex. Next one, please. This is their prize specimen. This is, again, is Tyrannosaurus rex, and it's in the rigor mortis position. What happens with a lot of these dinosaurs when they die, the muscles go into spasm and the tails curl up like this and the necks go back. And you could imagine that maybe something dramatic had happened to the animal, but no, it could have actually died of old age. And then that's what happens to them as they go into rigor mortis. Look at the size of these legs down here. Next one, please. This again is a smaller, this is more of a, if you've seen Jurassic Park with the velociraptors, this is something akin to it, except that's more of a bird head than a raptor head. But it's something which would run fast with a long tail. And again, that's the rigor mortis position. Next slide, please. Even the small dinosaurs are put into life-imitating positions. Next one, please. This one everybody knows, Stegosaurus. Even your kids know what this one is. This is probably the iconic dinosaur apart from Tyrannosaurus rex. Next one, please. And they also have marine dinosaurs in there too. This is what's called a pterosaur. But they've got it in a special room which is specially lit with special painting on the wall. You actually get the impression that you're underwater. And they actually suspend them from the ceiling as well. That was very difficult to get a photograph of the suspended ones, but absolutely magnificent. Next one, please. This is the biggest pterosaur in the world. It fills this room, and by the way, that's the beginning of the tail. And it goes through this glass cabinet out. So it'd be about that kind of distance, again, from here to the end of the glass cabinet. Apparently, it was vegetarian. Next one, please. I love this one. Here's a bird-like dinosaur coming to raid this here. Those are dinosaur eggs. They're real dinosaur eggs, fossils. Absolutely amazing. Next one, please. This is the biggest fish ever found. It's gigantic. That size, from there to about there, would be me, for scale. And inside this fossil, that is its last meal. This museum, I tell you, if you ever get anywhere near Drumheller, you must go and see this place. Next one, please. It has all kinds of things, not just dinosaurs. It's got these wonderful, wonderful plant leaves and so on, beautifully fossilized and preserved. The photograph here was taken from a slab, which actually is about the size of this entire wall. And I just picked that part of the slab to take a picture. Next one, please. Some of them are really delicate. You could almost pick it up in the woods around Gatineau Park. Next one, please. But I do have a criticism of the Tyrrell Museum. The explanations here were okay, great. You know, you could learn a lot about the fundamentals of dinosaurs. But what I didn't like was that sometimes I'd see something which really looked strange. This camel-like dinosaur, he was not a camel, not related to camels at all. It's a dinosaur. The explanation here is all about its legs and all about locomotion, which is good. But what the heck are these things up here? Surely those are the struts of some kind of a sail which the creature would have had on its back. It's not the backbone, there's the backbone. And there are the vertebrae of the backbone. This is something completely different. Not a word about it. The other thing that I was disappointed with was they do have a Burgess shale fossil exhibit. And it was terribly lit. What they were trying to do was imitate what a 19th century fossil hunter would have had in his office with these glass cabinets and wood cabinets and so on. You couldn't see a damn thing. Luckily, because I'd already been to the Burgess Shale itself, I wasn't too disappointed. But when I signed the guest book, I made that comment. The other strange thing is, as I said, this is a world-class museum. This must be the only world-class museum in existence that does not have a glossy coffee table book with photographs of its contents. I know, because I asked for one. I said, where is your contents book? And they said, no, we don't have one. But on the other hand, you're welcome to take all the photographs in the world, and it is beautifully illuminated. I kept 196 pictures from the museum. Okay, so from there, I got in my car and it was time to drive home. Well, I had the most fantastic weather from Ottawa practically all the way out to Washington State. While I was in Washington, it was blue skies all the way. It was absolutely wonderful. In fact, it was such nice weather that when I did the hiking up to the high points to take the perspective pictures, I had to choose my days, because at 33 degrees, I did not, in the shade, I did not want to be up exposed on the tops of those outwash channels. So I got in my car and I drove to Regina, and from Regina to Ottawa, it was low cloud and rain all the way. Alrighty, so let me conclude with this. This was one hell of an amazing trip. You can imagine, I prepared this in excruciating detail. You don't just drive out to a flat plain, which only has negative relief, and start wandering around on the off chance that you might actually find some hole somewhere or some channel somewhere. You have to know what you're going to look at. And luckily, I had two of the most amazing professional guidebooks, the size of these things, written by geologists who actually worked in Washington State, the professionals who had actually done the work. They have done a fantastic job of guiding you, telling you exactly where to go, what it is you're looking at, what the interpretation is. I'm not an expert in this particular field of geology, but I thought that they really convinced me that they were really onto it. They knew what they were doing. So I knew what I was coming in for. I'd even gone to Google Earth. You know, you can fly around in Google Earth in 3D, so you can actually get up in a helicopter, in inverted commas, and actually see what you would see if you were up in a chopper. So I knew exactly what I was walking into. I was really looking forward to this trip. Well, it was even better than I imagined. I found myself coming out to the edge of these canyons and looking down into the canyons and hearing somebody go, "Oh my God, what is this?" Well, that was me on my own. It was even better than I thought. So this was the trip of a lifetime. I'm really glad that I did it by driving across Canada. That was absolutely a lot of fun. Don't believe it when they tell you that the prairies are boring. It's not true. But do be careful how the others around you are driving. Thank you for listening. Let me wet my whistle, and if you've got any questions, oh, you got your question.
Yeah, so Simon, I was wondering again, I don't understand the mechanism for the vertical columns of methane.
If you've got a material, if you're a farmer and there's a drought, you go out into your fields, and how do you know that your fields are really in trouble? The soil is broken up into a series of polygons. And what's happening is that the soil is shrinking, not because it's cooling down, but because it's losing its water. And the way that shrinkage occurs in a laterally extensive material, where you can't just shrink at the sides. It's actually shrinking internally. And what happens is that points of shrinkage set up statistically within the material. So you've got a point here where everything's trying to migrate in towards, and a point here where everything's trying to migrate in towards, either by drying out or by thermally shrinking. And the ideal shape, in order to get the material to shrink around isolated points at equal distance from each other, is a hexagon.
And how does it go vertical then?
Oh, because you've got a thin layer. And so this point is actually a line. Everything's shrinking in towards this line. But then there's the next line is maybe only this distance away. Or alternatively, with those big ones, actually out on the other side of the car park. And that's what the mechanism is. So if you just want an analogy, just think of the way soil breaks up when it dries out and shrinks. Exactly the same thing.
So on your Mars photos, you pointed there are a couple of volcanoes, right? There's spots?
No, there are no actual volcanoes. No, you mean in the Badlands?
No. In the Mars photo.
Oh, yes.
Are those active volcanoes or?
They've been active recently. By recently, this is geologically recently. Geologists, planetary geologists, look at a planetary surface and they say, okay, look, let's actually look at the density of craters of a certain size. And they say, okay, let's now compare the evolution of the density of craters through time, through the solar system, with the same progression on the moon. Why? Because we've sent astronauts to the moon who brought back material from these impacts, and so we actually have dates, real dates from the moon. Now this is a little tricky because the moon is near the Earth, it's not further out. And then you've got another planet like Mercury, which is even closer to the sun, and the sun undoubtedly attracts a lot of these impacting materials. But if you just allow people to generalize, people can then turn around and say, okay, if we now look at the volcanoes on Mars, we can see that parts of the volcanoes are very old because there's lots of impact features on them. And some of them are quite young, geologically, because there's less impacts or even none. And they're talking about the last 50 to 10 million years. Now, all of the planets are 4.5 billion years old. So you can imagine that 10 million years ago is, and a planet, if it was capable on Mars of actually having active volcanism 10 million years ago, then it probably still is today. We have not actually seen any evidence, but it is possible that Mars is still capable of volcanism.
Are those pictures from NASA website? Are there devices?
Yes,
to send the picture back.
The ones from the ones off Mars, most of them are NASA, but the oblique perspective shots, those are the European Space Agency, and they are all real images taken by the more recent orbiters. And some of them are really high quality, really high quality. Still not high enough quality to see the small scale structures that I could see in Washington State, but they're breathtaking. And it is worth going to both the NASA site, going into their Mars section, and looking at things like MRO, which would be Mars Reconnaissance Orbiter, but also go and look at the European Space Agency site, because it's even better. What they've done is the Americans will release their images very, very quickly, and then they'll process them. But what the Europeans do is they hold on to them until they've got them just what they want, and they'll stitch them together to make a mosaic, and then they use computers to now tilt the image so that you actually get that 3D oblique perspective, and you can download the images on your computer and you can zoom in. And the details that come out, it's as though you were walking on the surface yourself. It is absolutely amazing. And the fantastic thing is they've got so much data, they haven't actually had time to interpret it. And if you go to both NASA sites and the European Space Agency sites for Mars, you'll see things which, well, I'll look at the picture and go, what? Why are they interpreting it that way? Or why are they even paying attention to this part of the picture? What about this over here? But even a non-geologist could look at these things and even aesthetically look at them and say, this is absolutely fantastic. Yeah. There's certainly a lot we have yet to learn about Mars, and even from the data we already have. A lot of it's sitting in archives, and they're publicly available archives.
Simon, is basalt easy to erode by water alone, or would there have to be some sort of water and sediment
Nope.
sort of...
Water's enough. Imagine, I don't know if you've ever tried to ford a river.
Okay.
You know, with the water up to your knees. And the water might be flowing at, let's say, 35 kilometers an hour. You'll have a lot of trouble standing up. And so you don't walk sideways, you do this and you creep across, and you've got a couple of poles. It's really difficult. Now imagine that water's 300 meters deep and it's flowing at 110 kilometers an hour. It's just like a wall coming at you. And it's turbulent underneath. It just pulls these things out. I mean, this is like pulling straws out of a bundle of straws. The whole bundle starts to collapse. If it was solid lava, it might be more difficult. This is why the computer simulations which are used to determine the Martian model of catastrophic flooding are really not very firmly grounded, because they don't know what the state of the lava is. You can actually go out to Washington State and see it. In fact, I took a photograph of a massive lava flow that had no fractures in it. It was the only one I found. That's why I took a photograph of it. Everything else was like this bundles of straws everywhere.
Simon, water moving that fast must have also produced a pretty loud noise.
Well, it must have been absolutely deafening, but I'm glad you asked me that question. If you're imagining, well, what would it have looked like if I'd been there? Well, number one, the water was flooding across this huge plain, so you'd have had trouble finding anywhere to stand. But let's put you up in a helicopter 15,000 years ago now. What you would have seen, because you're talking about 300 meters depth of water here, including 100 meters on the plain, so you can't even see the plain. So the cascades, the dry waterfalls we see now, were underwater. The bottom of the Cascade Cliffs was underwater. So what would you have seen? You'd have seen this almost horizontal surface of water rushing out to the west, to the Pacific. It would have been tilted slightly, probably about 1 or 2 degrees. Because it was going so fast, it would have had what's called standing waves everywhere. And locally, there would have been areas of turbulence. That would have been telling you that down below was dry falls. So you would actually have seen nothing. You would have heard one hell of a racket, but you would have actually seen nothing of what was actually going on in terms of the erosion. And all of this within 3 to 7 days, and then over.
Simon, I can't help but ask you the question, if you really went to Mars. You did, sort of, but if you really went to Mars, what would you like to do there?
I tell you, if I were to go to Mars, I would like to be in a position to supervise seismic stations on Mars, because the really key thing, for me, the next step is to look inside Mars. We've had all of these orbiters going around Mars, and I hope we have several more, and they've taken the most exquisite coverage of the surface. You can go down onto the surface of Mars, and you might be able to walk a few kilometers. As a professional geologist, my average traverse across the ground every day was 15 kilometers. They're really pleased at NASA that their Curiosity rover has now covered 15 kilometers in 2.5 years. To my mind, I would not go to the surface of Mars to look at the surface. I would want to make sure that the seismometers were working. Why? Because Mars has the most fantastic internal geology, which we can't see. Those big volcanoes, there they are, these ones here. They've been erupting for 3.5 billion years. There's no such thing as a 3.5 billion year long eruption on Earth. There's a reason for that. We have a thing called plate tectonics, where the continents move around and the oceans go down underneath and things get heated up, and so you get volcanism along the edges of the continents. That's what the Cascade Mountains are out in Western Canada. That's what Mount St. Helens is. It's one of these volcanoes that's along the Pacific margin. But on Mars, the volcanism has been in the same place. And not only that, but look, that's where they're all concentrated. This is the only other really big volcano on Mars, and it too has a really long history. So the big question is, what on earth could be going on inside Mars to feed volcanism, heat, volcanism, for 3.5 billion years in one place? That's what I would want to know. And the only way to know it is to actually look inside. And you look inside using geophysics, and you use seismometers. This is the same thing you use to actually record earthquakes on Earth, or to actually monitor the nuclear test ban treaty. But Mars will actually have Marsquakes. I mean, simply because there are impacts, or maybe there are actually some faults that are moving. And as you actually have an internal fault in any rocky planet, the planet rings like a bell inside. And what seismologists do is they listen to the sound of the ringing of the planet, and they can do all kinds of wonderful mathematical processing and so on, and they can then actually get an image of what the inside looks like. And I want to know is, what does it look like underneath this huge plateau with the biggest volcanoes in the solar system, all in one place and active for 3.5 billion years? That's what I would do.
I have a question from on NSN from Curtis. He's asking what the difference in altitude was from Lake Missoula to Pacific.
Now that one I can't tell you. But I can tell you this, and that is that when you're standing on that plane, things would have had to have rushed a long way west before you actually started getting down to a steep slope down towards the Pacific. But we're in the order of maybe 500 meters above sea level, something of that order. You know, we're not looking at something like the Colorado Plateau, which is several kilometers up.
I was wondering if in a lab we can create the erosional rates needed for the future.
Probably could, but the thing is, you've then got to have a lava flow in there,
Yeah.
and it's got to be at the right scale. And you saw the size of some of those columnar joints. I would think it would be very, very difficult. But we do know a lot about the carrying power of water. And there are assumptions that need to be made. You've got to know something about the depth, the speed. You also have to know something about the friction between the substrate and the water itself. But again, if you can actually walk out and touch the actual valley itself and the valley floor, you can actually work out the frictional rate. The problem on Mars is that we don't have good enough resolution to be able to look down in those valley floors and say, oh, we have observational evidence for the friction that might have been there. A friction is assumed. A slope is assumed. A speed of water is assumed. Depth of water is assumed. They simply assume the water filled the channels. In Washington State, we can show that it actually overtopped the dam channels and went up another 100 meters. So this is the issue. It doesn't mean that the Martian model is wrong, but it's certainly got a lot of holes in it. And one of the fundamental ones is how do you get something that big? And if they're going to use water to do it, and catastrophic water, where is that water going to come from? We know Lake Missoula existed, just the same way that we know that Lake Champlain existed around Ottawa, because we got the Leader Clay. And the Leader Clay, wherever the Leader Clay is, we know that that's the bottom to the Champlain Sea. And people who built their houses on it know all about it.
What's Leader Clay?
Leader clay is a very, very fine clay that is so mobile. It's sort of a clay version of quicksand, if you like. And the thing is even vibrations can set it off. You remember with the Wakefield train, when the rails disappeared over a segment, that again was because the rails were actually on the Leader clay, and the Leader clay just began moving down slope, just a 1 degree slope. So where was I? Oh, that's right. Now, in Glacial Lake Missoula, that's what they did in the 1940s. They went out and actually looked for evidence of some kind of backed up water mass. And they found clays and sands, which describe beautifully that blue area in one of the early slides, which is Glacial Lake Missoula. Jim?
Has anybody drawn a comparison between lava channels on the moon, like Schroeder's Valley, to these outwash channels?
Good question. This is actually where... Yeah, has anybody actually drawn analogies between lava-created channels on the moon and these channels on Mars? And they have. and not only on the moon, but also on Mercury and even Venus. And this actually is the fundamental underpinning to this alternative model, which is not really receiving good press in the scientific literature, but is not completely off the wall. The idea is, folks, if you're going to call upon water, then you've got a unique situation to Earth and Mars. But what about these channels on other rocky planets where no water was ever available, like the moon, like Mercury, like Venus, or at least the current surface of Venus? And so they say, well, if these channels could be carved, they're similar. They're long. They tend to get squiggly. Are they flat-bottomed with steep sides? To a degree. But this is the initial thinking behind the idea that maybe the Martian channels were themselves carved by lava. The big problem is with the lava interpretation for the erosion is, what do you do? How do you explain the sediments? The sedimentary islands, which clearly have no trace of lava related to them at all. They have to be related to water flow. And you saw the size of some of those ripples, the size of some of those islands. They are of comparable size to allow you to actually interpret the overall erosion, even of the bedrock, as by water.
We touched earlier on humans going to Mars to do this geology, but there's an enormous cost involved in doing that. Would it be more justifiable to send more machines to do that work for that amount of money? Would that be more productive than humans?
I think it is. I think it is, because if you look at all the breakthroughs, or all the steps forward, the leaps forward that we know with respect to, let's stick to Mars for now, with respect to Martian geology, all of it comes from these orbiting platforms. And as you move forward with the technology of the orbiting platforms, that's when we get the best leaps forward. We've put rovers down on the ground. I would iconoclastically claim that nothing any of the rovers has shown us has actually moved the science forward. All they've done is simply confirm that, yep, there was probably a channel here. Yes, there appear to have been some pebbles which were rounded off by flowing water in a channel. But the rover was sent down in the first place because you could actually see the channel from space anyway. I think that the sending of unmanned probes around the planets throughout our solar system, that's what's really energized planetary geology. Except if you want to see what's inside a rocky planet. And at that point, you've got to put something on the ground, because you can't read seismic signals from space, no matter how close you are. You've got to get down on the ground. And you need a number of these things. You need a minimum of 3 in order to triangulate to know a position. In reality, for a real scientific mission, you probably need tens of these things, maybe even something of the order of 100. But they're relatively cheap, because all you're doing is you're sending something which is robust enough to get there, crash into the surface, stick a probe into the ground, and then sit there and send you the signals back.
So there's no point where an astronaut geologist would be able to do something that we can't get a machine to do? Is there
No.
any point at which a human geologist would have to go there to do more geology?
Yes. If you turn the question around and say, well, can't we just get rid of geologists on Earth and do everything by machines? The answer there is very clear. No, the answer is no, and I'll tell you why. It's very, very simple. The machine is up there looking down, right? And I'm standing here looking at an outcrop. I can actually see it, the machine can't. Simple as that. I can actually get down on my hands and knees with a hand lens and actually see it. Now let's turn the question back to Mars. Yes. If I did my geology thing on Mars, what would I contribute? I might manage to get, let's say over a period of a year, I might manage to get a few traverses of the order of maybe a kilometer or so if I had a buggy. But then the problem with the buggy is you're not looking at the rocks. You're actually driving over them rather than actually looking at them, and you really should be walking over them. You couldn't cover enough ground in enough time to actually make a difference to the science in the lifetime of your science program. And let's remember, these days science programs which are getting government funding, I don't care what country it is, no government wants to fund a totally open-ended project. They want to know, where's this going? What are your results that you're actually expecting to get? And what's your time frame? So quite honestly, right now, I think the best thing that NASA could do is stick with probes.
So Simon, I'm trying to summarize in my head here. The duration of the drainage of glacial Lake Missoula, 37 days. So you said we understand roughly how big it is, okay,
Mm-hmm.
the size of it. We have evidence of the rate that the water was flowing out, for example, the rocks being sort of, I can't remember the term you used.
You call it shot out of a natural shotgun.
There you go. So we have evidence of we have an understanding of sort of the flow of water. Is that how they determined? Was it just that alone? Were they able to determine the rate of?
No, the slides that I skipped over because I was looking at my watch and thought I'd better sort of move through a little bit. There's a thing called the Cascade Falls, and no, the Staircase Falls, and what it is, it's the slide's still up.
Yeah, I know which slide.
I'm trying to understand what was the most telling piece of evidence that said here's why it was 3 to 7 days in duration.
Oh, you know your volume of water. You certainly know your surface area. You know how much water you've actually got to get out there. They need 700 meters in terms of source depth in order to account for the depth of water you've got downstream. They know speeds, in part because of the erosional power they can see and the carrying power they can see. There's also a thing, as I said, this Staircase Falls, where you've got a plateau at the upper end, upstream. You've got a slope with a series of cascades in it.
Okay.
And it goes down into one of these coulees. So you now know a slope. And you know what the thickness of the water is coming off the top. And as it goes down this slope, since you can actually see the slope, you can then assume reasonable values of friction, and you can actually get a speed for the water. So there's direct observational evidence for depth of water, its carrying power, its speed, and its source.
So it's calculated into 3 to 7 days. Based on
Well, you've got to get that water out of the lake and at speeds which can actually create the erosion, and your water is finite. So after 3 to 7 days, you've run out of water, in a nutshell.
Do you know how long Lake Missoula existed before it drained?
Nice question. There's an argument in the geological community that actually works on this stuff. This is not the only catastrophic flood. This was the big one, and this was the last one. But they figure that some of these floods probably actually occurred. In other words, ice dams formed, glacial lakes formed, actually through the Ice Age. And the big argument is, among the professionals that work on this, how many of them were there? Now, there are some that say 40. And get ready for this one, some that say 1,000. Quite how you track 1,000 of these, I do not know. But you remember that hanging valley that I showed you above the main valley and said this is earlier and this is later? Well, some are going to say, well, hang on a minute, these are different periods. It could be, or it could actually all be one or part and parcel of just an ongoing story. So that's the one, that's right. So it depends. If somebody wants to interpret this as being thousands of years or even 1,000,000 years older than this floor here, then they've got two periods completely separated in time. Somebody else that says, well, hang on, no, this occurred on day 2, and then this occurred on day 3, then you've got an ongoing sequential event. And that's why there's this debate. And if they're arguing about 40 to 1,000 and can't actually come to a reasonable conclusion on that, gives you an idea of how loosey-goosey maybe the attribution of features to episodes really is.
So Lake Missoula was, the source of the water was what, melting
Yes,
glaciers?
that's right, yeah. And the reason it was held up was because of the mobility of ice at the edge of the Laurentian ice sheet, or the Columbianite ice sheet, I guess it would be called. Yep. So the idea is, as the ice sheet was moving around towards the end of its life, that it was creating dams, breaking them, creating more dams, breaking them. But the only one that we've really got a detailed story on is the big one. That's this. Reputedly the last one.
So that lake could have existed for, what, 1,000,000 years before it drained? Like, you know, I mean, obviously more.
I would doubt it. Ice is pretty mobile. 1,000,000 years, that would be half the Ice Age. And remember that during that 2,000,000 years, you had ice advances and ice retreats, what they call interglacials. In fact, there are some that say that we're just living through another interglacial right now, and that wait long enough and there'll be another glacial advance, and we'll be back into an Ice Age. Now, we're talking those are actually proposals. They're talking about 50 to 100,000 years down the road. But that's the kind of time frame for going from glacial period to an interglacial period. So the ice would have been mobile. And I would doubt that glacial Lake Missoula could last for that long. It's probably of the order of maybe 1,000 years. Oh, and the important thing is that on Mars, when people are talking about a source of water to port this catastrophic story off to the planet Mars, one of the big objections is, well, if you go to the upper ends of any of these outwash channels on Mars, where is the evidence for a lake that would actually have catastrophically flooded across the land? We can easily see geological evidence on Earth for these things. Glacial Lake Missoula and Lake Champlain, they're not the only examples. There are many examples in recent geological history all over the globe where people have established that there was an old lake here. And you would be able to see it very easily with our current orbiting platforms, and they're not there.
Just wondered if you could infer the length of time that that lake existed by the sediments. Is there any way you can measure the sediments?
Yes, they probably could. I mean, if there was really fine scale lamination and they could determine that they had a good model to explain it, then they could actually count that out. I don't know the details of whether they've actually done that. Yeah, because these guidebooks here, which were my main source of information, they're really focused on Washington State and on the erosional remnants, etc.
So why isn't there no drainage lake on Mars?
Well, the thing is that these channels formed on Mars, as I said, if you imagine the life of the solar system, the life of planet Mars as a hockey match, they formed at the halfway break. But the trouble is that by that point, Mars had already lost its magnetic field. Its atmosphere had already collapsed. And therefore, liquid water was not stable on the surface of Mars at that point. So if you're going to propose a lake on Mars, you're much better off going to sometime in the first quarter of the hockey match, in the first billion years. And there is evidence for surface water. People have even suggested that northern plains, the blue area on the original, the blue stuff up there, people have even suggested that was, in fact, an ocean bed. Now, there's still a debate as to whether or not that actually, that story holds. Personally, I think that there's pretty good evidence that there was standing water there. But that would have been in a very early part of Mars's history. These channels have formed later. So the only real place that you could realistically suggest getting the water is out of the ground. And as I said, the problem is that getting it out of the ground is not the same thing as pulling the plug on a dammed lake. There you could get something catastrophic, but getting water out of the ground catastrophically, and in even way bigger volumes than in our terrestrial example, it just gets out of hand. And that's why it's not out of the question that some people come forward and say, well, maybe it was actually erosion by lavas. I don't think that lava erosion story works, though. I think there's good evidence against it.
In passing earlier, you mentioned glaciers on Mars.
Yes.
I was wondering what other evidence there was.
You can actually see them.
Oh.
But they're actually rock glaciers now. In other words, imagine, you must have seen pictures of the Swiss Alps or pictures of the Rockies where there are glaciers in the valleys. And sometimes you'll actually see the long, skinny glacier coming down the valley. And on either side are long trains of rock which have fallen down off of the cliffs. And sometimes two glaciers will meet, which now means that the rocks which were on the edge of the glacier are now in the middle of the new merged glacier. So you can get all kinds of rocks all the way through the glacier. It also turns out that you can actually get creeping ice with anything from 0 rock content right the way through to lots. I won't put a number on it, but it could even be something like 60-70% rock in a moving ice mass. Now, that thing stops. You destroy the atmosphere of Mars. Water begins to sublimate. Ice sublimates. And so you end up with this, what looks like rock. But when you look from space, you can actually see that what would have been the surface traces of these rocks on the top of the glacier as glaciers merged. You can actually see things like this. You can actually see U-shaped features, really long, high amplitude U-shapes, which are the glacier noses creeping down a valley. Now, it's not ice at the surface, it's the rock that's sitting on top, but underneath, you can see the ice. You perhaps heard of ground penetrating radar. You can actually use the radar technique and you can actually look into rock. Now usually it's done when you've got a machine which is actually sitting on the surface and you can't look down very deeply. We're talking, I don't know, maybe in the order of tens to perhaps 100 meters, but from space they're actually able to do ground penetrating radar on Mars and get as deep as at least a half a kilometer, maybe a kilometer. They're not looking through solid rock. They're actually looking into these rocky glaciers and they can see layering. They can actually see structure. They can see folds and faults in what would actually be the glaciers. Now, they're covered with a lot of dust, a lot of sediment, and a lot of rock. That's why they're preserved. But there's evidence for glaciation. And the wonderful thing about the evidence for glaciation on Mars is there's as much evidence for glaciation at the equator, or near the equator, as there is at the poles. And the reason is that Mars, in its wobble, Earth wobbles as well, but the Earth's wobble on its own rotation axis is controlled, dampened by the existence of our moon. Our moon, compared with the size of our planet, is huge. It's as big as the moon's going around Jupiter, but Jupiter's even is huge in itself. So our huge moon stabilizes, and so we wobble like a top, but very gently. Mars wobbles like this on a scale of 10,000 to 100,000 to 1,000,000 years. And so you could actually end up with the equator actually essentially being polar. And you can see a good evidence of glaciation on Mars. In fact, there's an entire sub-science of glaciology, which is Martian glaciology. You can actually have a lifetime research career studying the glaciers of Mars. Now, in answer to the question, what could you do if you actually went there on the ground? Now, if somebody says, look, you know, I actually know how glaciers form, and here's a glacier, and I'm going to go and have a look at this glacier on Mars, and I don't actually need to cover the whole thing. I'm just going to do a few transects across it, widely spaced, but I already know everything about glaciers anyway, so I know exactly what I'm looking for. Then yes, under those kinds of circumstances, yes, a geologist on the ground could make advances in science. But that's one hell of a cost to get somebody up to do that kind of thing. And frankly, we haven't used up the potential for ground penetrating radar. Alrighty. Thanks again for coming, and thanks again for listening.